Okay, let's try another one of these pharmaceutical problems. Again, one of these is on your test, so I really want you to understand this. It says a pharmaceutical company has a test that is 95% effective in determining whether a person has a certain genetic defect. However, the test may give a false positive result in 4% of the cases. Suppose this particular genetic defect occurs in 2% of the population. Given that the person tests positive, what is the probability that the person actually has the defect? So let's first look at what they want. They say, given that the person tests positive, so our denominator, anything that's given as our denominator, we know that they have a positive test. What is the probability that the person has the defect? So we're going to say has defect and tested positive. Okay, so that's how we're going to determine it. The total is what's given to us is that they've tested positive, and then we only want has defect and positive on top. Okay, so let's start off with our tree. Again, here we're going to have a defect or no defect, and then we're going to have tested positive or negative. Okay, I want you to remember this first one would be accurate. They have the defect and it tested positive. The second one would be called a false negative. They have the defect, but it says negative, so the negative result was false. The next one is no defect in positive, so that's a false positive. False positive is right there, no defect in positive. And then the last one is accurate. They had no defect and it tested negative. So let's see if we can read this. It says the test is 95% effective in determining whether a certain person has the defect or not. So if it's 95% effective in determining if they have the defect, that means the defect positive, the accurate result, is 95%. Well, if 95% have the defect, or if it's 95% accurate, that means it's 5% inaccurate when they have the defect. Okay? Let's look at the next one. It says the false positive might be 4% of the cases. False positive is 4% of the cases. So again, false positive would be no defect positive. So that's 4%, so that's 0.04. Well, if 4% are false positives, that means that 96% then have to be accurate negatives. Okay? Let's look at this, and it says the defect is 2% of the population. So if the defect is 2% of the population, then no defect has to be 98% of the population. So that's how I'm getting all my numbers right there. And then again, to get the totals, I'm going to multiply them together. So this is 0.02 times 0.95. This is 0.02 times 0.05. This is 0.98 times 0.04. And the last one is 0.98 times 0.96. But because this is a given probability, a conditional probability, I don't need to consider all four of these. I only need to consider what I want. So in the denominator, I wanted when it tested positive. In the denominator, I wanted when it tested positive. So let's look at these branches. When did it test positive would be when they had the defect in positive, and when they had no defect and it tested positive. So it seems like my numbers there would be, I'm getting 0.02 times 0.95 is my first one, plus the rest of them, which is the 0.98 times 0.04 times 0.04. And then in the numerator, I want to consider how many had the defect and tested positive. So that's just the 0.02 times 0.95. So I'm going to put that into my calculator, 0.02 times 0.95, all over 0.02 times 0.95 plus 0.98 times 0.04. When I do that, I'm getting a decimal value of approximately, I'll do 3 decimals, so 0.326. How about that? But then let's write it as a percentage because theirs was written as a percentage, so that's approximately 32.6%. So let's reflect on what the heck we just said. We just said if they test positive, what's the chance that they actually have the defect? And the answer is there's only a 32.6% chance that they have the defect. So I want you to think about that. The drug company is stating that it's 95% effective, Yet, if it tests positive, it's only 32.6% effective. What does that mean? When someone gets a positive result, only about 1 out of every 3 people, approximately, are actually positive. So that means out of 3 people, they're scaring the living crud out of 2 of the people, and only one of the other one person actually has the defect, whereas 2 are getting scared because it tested positive, but they don't have the defect. So that's a very, very, very low number here. The only good thing is if this is a serious life-threatening defect, they are catching 95% of the people who have the defect. Even though, yes, they are scaring a lot of them, they're catching 95% of them that have the defect. So that's a good thing in that sense. That 95% is a good thing, but the problem is their false positives here are extremely, extremely high. Okay, let's move on. The next one's not really a problem that you have to do, but it's really kind of a cool thing. It's about sharing birthdays, and I want you to read through this and then look at my solutions to see the actual answer, the solutions that I've posted online. But it gets you to the idea of how can you guarantee 2 people have the same birthday? Well, technically, to guarantee it, 100% guarantee it, you would need 366 different people unless one was born on a leap year. You would need 367, but you would need 366 people because there's 365 days a year. So to 100% guarantee that you have 2 people in the same room with the exact same birthday, meaning month and day, you would need 366 people. But what this gets at is how many people do you need in a room to have a probability? So that's a probability of 1. You need 366 people. How many people do you need to have a probability of 0.5 or a 50% chance? And so if you go through and you do the math and you read through this problem, you're going to come to a conclusion that you need approximately, I think I got about 23 people is what that I needed. All you need is 23 people in a room to at least have a 50-50 chance. So what you'll see is a lot of math teachers, when they teach a probability section, if there's about 30 students in the class, you have a pretty dang high chance of 2 of those students having the exact same birthday, same month, same day, even if there's only 30 people in the room. So it's a 50-50 chance if you have 23 people in the room. And if you work through this and look at the solutions online, it's going to show you how I worked through that and how I got those numbers. So it's just kind of a fun excursion for you. It's not on this last part is not on the test. It's not any problems that you have to do. Just kind of very interesting problem for you to look at.